now you should be used to saying, I understand that there are atoms. I can find which of the elements I'm looking for on the periodic table. And there's some relationship between neutrons, protons, and electrons. But really, up until the Dalton's atomic theory, we didn't know what was inside of those atoms. We didn't know there was evidence for electrons or protons or neutrons. So how did we get to know that? I'll make this as quickly as possible because it is spread between these chapters. You're going to see the reading marks here where it comes from 9, 10, 11. But let's see what discoveries led up to the understanding. And we'll start off with the electrons. Okay, electrons, once we knew they existed, they could prove that the atom must not be neutral because there's something that held them there. So the protons and electrons are the same story. First of all, we understood already that light was a wave. Huygens in the 1600s was showing that diffraction and refraction were possible only if it were a wave, and we talked about those last unit. Some mathematicians were studying in the mid-1800s, after Dalton, the math that would later be used to describe what those waves might look like. Okay, so that had to always happen before the science could get there. But Crookes was a scientist that had said, wow, if I take these tubes and I kind of suck a little bit of a vacuum on there and I hook up a battery to those, so we needed to have batteries, which were the volta, galvanic cell, or the voltage pile is necessary, that he saw that there would be a little stream of light that would go from one wire to the next. And he couldn't figure out what that was, and he postulated that was maybe a negative charge that was jumping between those because of the way the battery was hooked up. Bunsen was studying the same phenomena of that light coming off of different atoms, and he needed something, instead of trying to find them in a gaseous state in a tube, he just heated them up in a super hot flame, which is his own design, the Bunsen burner, and then he would look through the light that was spread out using, we talked about how diffraction spreads certain wavelengths out more than others, but he would send the light through a prism and then look at it in like an eyepiece or a little microscope, and he saw that every single element gave off a different spectra. Every atom gave off its own unique spectra. He was trying to figure out why, and why would they only certain wavelengths, not the full color of the rainbow. Okay, so that was at late 1800s. It was about the same time, just about before the turn of the century, that Thomson came through and said, you know what, we have some experiments. We can take that beam and we can see if it's influenced by an electric field, and he saw it was. You also could see if it was affected by a magnetic field, which we know traveling electrons, traveling current, interact, and they have their own magnetic field. So he was able to show, I think I know, I can figure out what the charge of that beam is. The trouble was if it was a bigger particle or a smaller particle, it would curve less, and he could only tell if it had twice the charge, but it was twice as big as well, it would curve the same as if something half its size and half its charge would. So he only knew the charge to mass ratio. And he still was working hard to figure out what the charge on the smallest particle of charge was, the electron. But by showing that this was a charged particle, he also implied that it must have left the positive behind, so that both the proof for the negative and the positive, because the negative exists, the positive must have. The protons and electrons were discovered, let's say, by Thomson, and he gave them that charge of negative charge. Going back to the light issue, Max Planck was trying to study these same things. He was a German scientist in 1900 when he first discovered or tried to define this, is that he said, yes, if I take light off of a hot light bulb, something that's really hot, or the sun that's got real condensed atmosphere, something where all the atoms are really touching but it's really hot, they'll give off every color possible. But when you get to these conditions where you sort of have a vacuum and you're looking at fluorescent lights, or you saw where you heated up atoms that were inside a flame that weren't necessarily touching each other, they gave off these distinct waves that had very sharp energies. He said that must be true because that light that's being generated by an atom that's been heated must give off light in a quantized way, a set amount. And they can't give off any others. So you saw that hydrogens or any of these have distinct colors and not any others. He was trying to figure out why that was. He wasn't sure, but he came up with saying, I know what the energy of every one of those light is. Red is going to have a certain amount of energy, and that's the formula for it. You take Planck's constant, which is some number times 10 to the minus 34th, a super small amount of energy, times the wave frequency. We already know that frequency is what determines light's color, and you can determine how much energy there is. The more waves you have, the more light energy it has. Ultraviolet has more waves and it causes sunburn. Infrared is less waves and it only feels warm if you see it infrared light. Okay? So his idea, though, that light has to be quantized. You can't have a continuous set from light coming off of a gas now, not from light from a heated filament, was unique. It was a new idea. And some of the early scientists that you're going to recognize, Einstein, for instance, started to study that. And he said, well, let's take a look at then this different colors of light. And if I shine that onto a metal, this is going to be called what your, on your ceiling might be as a photoelectric, a cell or a solar panel. Certain light doesn't cause electrons to jump off of it at all. That's like trying to push on some electrons on the surface of a planet and try to launch them into space. If you don't give them a big enough push, they don't leave the surface. Okay? But when you finally do push them hard enough and they do fly off into space, they start electrons flowing through, like a wire, for instance. That's called current, and they can see those. But it took a minimum color before the electrons started to flow. Any more energy color, any higher frequency color, would eject those off, and they would have even higher voltages coming off of that metal. Another way to think about those is even as light is being shined with more and more intensity, more and more beams of light are hitting there, as long as it's not the right amount of energy, no electrons leave, no matter how many light beams you shoot. But once you get up to the right frequency, the right color, you'll knock electrons off, and depending on how many light beams you shoot in, like this is much more intense than this yellow is here, this more intense yellow, every light beam knocks an individual electron off. So that Einstein was able to show that these individual light beams were interacting with individual electrons, and they gave proof for what Planck was talking about. The quantized amount of light interacts with a quantized amount of matter, electron, and they are able to then eject them. And so that's what he got a Nobel Prize for, is the photoelectric effect. Millikan shortly after that did figure out what the charge was by spraying a bunch of oil with electrons on it, just like you'd take and rub balloons in your hair, but these little drops of oil then were suspended in an electric field. And he could see that he could stop certain ones, and others would fall at 1 meter per second, 5 meters per second, 10 meters, but nothing in between. And so he reasoned the only way that those speeds would all be, like 10 or 15 particles fell at 10 meters per second, 1 or 2 fell at 1 meter per second, is that the charge were some individual amount, and he was able to calculate those. So altogether, he was able to figure out what the last charge of an electron was, and that was the story of understanding the electron and its charge.